and welcome to the UNU-INWEH public event, the Science Talk. I am your host, Professor Grace Oluwatoya. Before presenting our distinguished speaker for this morning, please note that there will be an interactive session at the end of the presentation. At that point, there will be room for comments, question and answers, and any other contributions you may have. Please type your questions or comments in the Q&A chat box, and we will pick them up from there. Thank you. The topic for today's talk is environmental predictions for water sustainability. In other words, how do we develop the next generation solutions to predict water futures? To do justice to that topic is Professor Martyn CLARK. Who is he? Professor Martyn is the Executive Co-Director of United Nations University Hub at the University of Calgary in Canada. He's also the Professor of Hydrology, School of Engineering at the University of Canada. His research focuses on advancing the science and practice of environmental predictions. His research group has built mechanistic terrestrial systems models for many applications like environmental forecasting, climate impact assessment, and health system predictions, to mention a few. He was elected Fellow of the American Geophysical Union and was the previous Editor-in-Chief for Water Resources Research. He has authored and co-authored over 200 journal articles since receiving his PhD in 1998. So who better to talk to us on environmental predictions for water sustainability? So Professor Martyn CLARK, you are welcome. I yield the floor to you.
Okay, well, thank you very much for that kind introduction, Grace. Before I start, I would like to respectfully acknowledge that I live and work on Treaty 7 territory and the homeland of the Métis, the Tsuut'ina, the Stoney, and the Blackfoot. I thank these nations for their care and stewardship over this land and water, and I pay my respect to the ancestors of these places. I wanted to start to provide a little bit of background as to where we're at the University of Calgary. We're very proud to be a hub for United Nations University. The focus of our hub is to empower communities to adapt to environmental change. We're delighted to welcome to the faculty a new Canada Excellence Research Chair on Indigenous ways of climate and water sustainability. Her name is Deborah McGregor. She's one of the cluster leads in the UNU Hub, and she started at the beginning of July of 2024. So we're delighted that she's joined us. The university has multiple research chairs in water across multiple faculties. The university's been investing a lot in transdisciplinary scholarship, over $19 million in new faculty hires. A lot of work on technological innovations at the UNU-INWEH facility, a lot of work in the Canadian Rockies on mountain watershed focus, and some of our faculty, Kerry Black and Fred Rona, are UNESCO chairs in mountain water sustainability, so we're connecting the work with them. We're working to build cooperative institutes. I'll talk a little bit about our collaboration with the USA on hydrological prediction. And we're working to expand partnerships with the City of Calgary, the Government of Alberta, federal agencies, Indigenous communities, and industry. These are some photos here from the launch for the United Nations University Hub. We launched on the 13th of December of 2023. We had a wonderful ceremony. And this is on the left, upper left here, is the signing of the Memorandum of Understanding with Dr. Kaveh Madani and President of University of Calgary, Dr. Ed Macaulay. On the bottom right is a lot of the water faculty who have been engaged in developing the UNU hub. What we're interested in is building models to simulate dominant processes across different environments. What we do is we build mechanistic models of terrestrial system processes for large geographical domains. And we build these models so that we can predict floods and water availability on timescales from seconds to seasons, and predict threats to water security on timescales from decades to centuries. A lot of our work uses big global data sets to provide information that's suitable to solve local problems. We're building open and reproducible model agnostic workflows to increase the efficiency and effectiveness of the modeling that we're doing. We're building data agnostic workflows to enable using a lot of our local data to improve model predictions. And a lot of our work is centered on high performance computing facilities so that we can address a lot of the next generation of hydrological prediction problems. Our focus more generally is to develop numerically robust terrestrial systems models that can faithfully represent the dominant physical processes across continental domains. So we're going through the work. I'll talk about some of the work that we've been doing in Canada, some of our collaborations with the United States of America, and then some of the work that we're doing to build a global community of practice in hydrological prediction. So the outline today, I'm going to really focus on two themes. The first themes is going to summarize some of the research progress that we've made in environmental prediction. And the second theme is to talk about what some of our future plans are. So in terms of our research progress, a lot of our work has been to improve modularity and interoperability of models. I'll talk about why that's important later, but just touching on it now, the modeling problems that we're being asked to solve by our governments are often too big for a single modeling group, too big often for a single agency, and sometimes too big for an entire nation to solve. So what we're working towards is a global community of practice, so that we can build computational ecosystems that can take advantage of the unique data, knowledge, and expertise from research and operational groups around the world. I'll touch a little bit about our work to improve the robustness and efficiency of the models so that they can be applied effectively on a global scale. I'll talk about some of the representation of physical processes. I'll give a couple of examples, and the examples that I'm going to highlight will show how it's important to bring in local knowledge in each of the regions, where the model is applied. And then I'll end with some of the challenges that we have to develop models of everywhere. So in terms of the modularity and interoperability, the problem that we have, as we've talked about in some of our opinion papers in the past, is that there's a glut of hydrological models. So there's often the joke in hydrology that every hydrologist has got their own model and some have got two. And in many cases, there are more algorithms, there are more models available than there are algorithms to populate them. So the same algorithms are used across multiple models. So the challenge is really to focus more on the economies of scale, so how we can define a master modeling template from which existing models can be constructed and new models derived. The hydrological sciences community has published a number of papers in this area, and it seems when you're looking at these papers that everybody has got their own idea as to what the appropriate path forward is for the community. But if you step back and look at those papers, you can categorize the contributions into different groups. So what some groups are doing is they're saying, well, okay, how can we have multiple land models that work together in the same framework? Other groups, they might be developing a crop model or a ecosystem demography model to represent the succession of vegetation over time. There's shareable model extensions that may overlap with part of our model, but provide new model capabilities if we integrate those new concepts in a host land model. We can have multiple representations of a model component, so multiple representations of a snow component, a soil component, etc. Or we can have multiple parameterizations of a physical process within a state equation. So the challenge that we have when we're threading that needle is to bring together the multiple models that work together in the same framework and multiple parameterizations that can work together in a plug-and-play environment to design a template that enables the different modeling groups around the world to work together more effectively. When we're thinking about that, we're thinking about that in both space and in time. So in space, what we're thinking about is how we can discretize the landscape in general ways, defining a hydrofabric across the globe to discretize the globe into subbasins that we can use for modeling. And then each of those subbasins have different land units to represent the processes that are important to us. And then in each of those land units, thinking about how we can bring together the vertical energy and water balance for different vertical subdomains within the system: vegetation, snow, and soil. We may have state equations for hydrology, thermodynamics, and biogeochemistry, and flux calculators that are estimating, say that in vegetation, for example, the liquid flux through the vegetation canopy, the energy fluxes in the vegetation canopy, and the biogeochemical fluxes. When we're unifying the model physics, we've got a very general problem formulation where we've got the hierarchical approach where we're very carefully discretizing the model into subdomains and state equations. And when we're being very deliberate in that way, that gives us the flexibility to use different coupled equations for a model subdomain, different conservation equations for a different state variable, different flux parameterizations with a given conservation equation, and different numerical methods to solve the model equations. So by thinking very carefully about how we can define a master modeling template, we're able to bring together the contributions from different modeling groups around the world. We're moving forward with unifying the model physics, and where this is a little bit geeky, but it's showing how we're working with a lot of the software engineering community to have object-oriented approaches that follow specific templates, so that if everybody uses these templates in the way that they build their code, the different modules that we develop, the different physical parameterizations can be effectively shared with modeling groups around the world. When we're working on a global scale and when we're working with so many different physical processes, we also need to improve the numerical robustness and efficiency. So here's our general modeling template that we have. And really, this is just another differential equation. So we're interested in how the change in this state with time is equal to the fluxes at the boundaries of the control volume. And when we separate concerns in that way, that enables us to bring different communities together so that hydrologists can worry about how to compute the fluxes in the system and numerical analysts can worry about how to obtain the state. So when we do that, we've now been able to incorporate a third-party numerical solver, and we have a lot of computational hotspots across the domain, which is showing the areas where the model is taking a long time to complete. That's primarily the mountains, which is providing us with new challenges as to how do we balance the computational load across our domain so that we can run our models on supercomputers. What we see when we've got these computational hotspots is that we have a straggler effect where there can be some parts of the domain that take longer to complete than other parts of the domain. And we need to dedicate more resources to those parts of the domain in a more agile way. So this is what we've been doing with the actors model. It's used by Starbucks and other people as a more agile approach to parallelization. So we're getting much better load balancing here. This graph that I'm showing here is the time that it takes the model to run on the x-axis, and the cumulative run times, which are the lines here, is showing that the actors model, the more agile parallelization method that we have, is a lot faster than some of its competitors. So by doing that, I know that was a little bit technical, but I kind of wanted to show, some of the details of what we were working on. We've really separated the concerns, and we've provided entry points for community members to contribute their unique expertise. So when we're thinking about the way that we've got the hierarchical organization of the model, we've separated out the temporal evolution of the state equations from the flux calculators. And what that's meant is that we can have the applied mathematicians come in to our model ecosystem, contribute their unique expertise, and make advances in terrestrial systems models in ways that they've been unable to do so in other modeling environments, because the physics of the model and the numerics of the model have been too closely intertwined. I want to talk briefly about how we can improve representations of physical processes. I'm going to give a specific example for North America, but the example that I'm giving can also be relevant for many other parts of the world. The problem that we have in North America, the prairie potholes, and the prairies, they're characterized by numerous land depressions. And it's been very, very difficult for a lot of models to provide adequate simulations of hydrological processes in the prairie pothole region. The prairies are often known as the graveyard of hydrological models. This can be true, or this can be illustrated if we look at this plot here. What I'm showing here on the left is the skill of a machine learning model across the contiguous United States, showing the Nash-Sutcliffe score and the peak timing. Better models, and what we're seeing is that the machine learning models perform worst in the prairie pothole region. And we also see similar results when we're looking at the Nash-Sutcliffe score when we're using a mechanistic model. In this case, we're using the model that's used operationally to produce streamflow forecasts by the National Weather Service river forecast centers across the country. And also the mechanistic model performs worse in the prairie pothole region. The processes that are important here is it's the temporal dynamics of contributing area. So in a lot of environments where we apply our models, the contributing area is fixed. We've got the drainage area, and the drainage area doesn't change with time. And we can easily calculate, the water balance and the energy balance over a river basin. The challenge that we have in the prairie potholes is that the potholes act as gatekeepers, and the catchment above the prairie pothole doesn't contribute flow until the prairie pothole is full. This is the fill and spill process. So what we have, in contrast to a lot of basins that we apply our models around the world, is that we've got temporal dynamics and the contributing fraction of the catchment. So this is an example of a precipitation event where we're gradually getting more contributing fraction of the catchment during a precipitation event as the prairie potholes are filling. But then we've got a lot of really interesting hysteretic effects, is at the end of the storm, we can get a tiny bit of infiltration out of the bottom of the prairie pothole and drainage from the bottom of the prairie pothole, a tiny bit of evaporation from the prairie pothole. And what that means is that the water level of the prairie pothole drops below the sill, and that prairie pothole is not contributing flow anymore. So that means that the contributing fraction effectively goes to zero, and then we don't start the hysteretic loop again until we have another storm. So this is something that's really missing from a lot of legacy models on these types of processes. There's simple ways of coding up these processes and incorporating these processes and models, but we need to go into this region and other regions around the world and ask, what are the dominant processes? Are the dominant processes missing from our models? And how can we do a better job of including these dominant processes? The code has been developed. I'll just gives an illustration as to what we're doing here with this code to incorporate it in time-stepping simulation models. We've got 3 different versions of the code. The first is a version where there aren't any potholes. The second is a version where we've got non-hysteretic potholes. And the third is where we've got hysteretic potholes. This is the HDS algorithm that we're showing. Our measure of model performance is the Klein-Gupta efficiency. And higher versions of the Klein-Gupta efficiency, as we're getting the Klein-Gupta efficiency to 1, represents a better model. So we can see that when we're representing the temporal dynamics of contributing areas, we're improving the model. And when we explicitly represent the hysteresis, we're improving the model further. So this is where Mohammed Ahmed, and we're in the midst of making this algorithm, this model agnostic algorithm, available to modeling groups around the world, and it's already been incorporated in 3 different hydrological models. So back to our master modeling template. Before, I showed how we could have an upland land unit within our hydro fabric, and think about the now that we've got the prairie pothole algorithm. This includes the wetland component of our model. And the nice thing here again is that we've separated the concerns so that people with experience in wetlands can just focus their attention in this part of the model and work together as part of the community to advance hydrological modeling capabilities for all. The final thing that I wanted to talk about, and I'm not going to be showing many figures on this, I was going to want to touch on the various elements of this, is how we're taking what we're doing and thinking about how we can develop models that can be applied everywhere. So there's a lot of the steps that we think are important. The first is to provide a synthesis of process understanding. So I mentioned that when we're going into specific environments, we've got new processes that we need to incorporate. That's the prairie pothole example. We need to provide a synthesis of our process understanding across continents and across the globe, so that we can understand what processes need to be incorporated in the model and how we can make that happen in a global community model. So as part of our synthesis of process understanding, our goal is to narrow the gap between our theories and our model equations so that the model equations explicitly simulate the processes that are important in the region where the model's applied. We, of course, define the model equations. The key step for us is to implement those model equations in the computer. This is really thinking about the community. How can we have an implementation of the model equations in the way that improves the modularity? That's the separation of concerns that I mentioned, so that people can easily use their expertise in a specific part of the model, and do it in an interoperable way. so that we can effectively share code and concepts across different model development groups. What we see from a global hydrology perspective is that it's rare for a modeling group to be excellent at everything. And normally a modeling group is really excellent at a subset of the processes in the model. So we want to be able to cherry pick and take what's excellent by one modeling group, combine it with what's done very well by another modeling group, and bring that all together in a broader modeling ecosystem. Once we have the community numerical model, the collection of process modules, we need to configure instantiations of those models to answer specific questions. So the challenge here is to investigate how and where we can incorporate algorithmic simplifications of varying complexity to represent the limited knowledge of hydrological processes and parameters. It's all very well to think about how we can deliberately, build the models, but often when we get to the step of applications, we're dealing with a huge problem of data scarcity, and we need to not only design the model that represents the process in the region that's applied, but also be cognizant of the data that's available and ensure that the complexity of the model is supported by the data that exists. A lot of what we're doing is not so much, as should be clear from the slides that I've been presenting so far, on each of these steps, but it's the fuzzy middle, it's the interfaces between all of these steps where we're putting a lot of our effort. So how can we narrow the gap between theories and model equations? How can we improve modularity, interoperability, and robustness? And how can we improve our workflows, our parameter estimation, the way that we evaluate models to provide hydrological modeling solutions that can be applied more generally? That's really focused on the research progress. Some of the considerations that we're embroiled in to try and develop solutions for community modeling everywhere. What I want to talk about now is what some of our future plans are. Some of what we're doing in Canada, how we're collaborating with the US, but also how we're beginning to take what we have now and pivot to think about how we can develop models that are applicable everywhere in the globe. A couple of, well, gosh, I think it was just a year ago now, we were working in Canada, and we collaborated with the UNU like senior fellow Bob Sanford. Bob Sanford is actually my neighbour. He lives in the same neighbourhood as I do in Canmore. We speak often. So Al Petronero, University of Calgary, I was at University of Saskatchewan at the time, collaborated with Bob to think about what was required to really push things forward for environmental prediction in Canada. The need that we recognised is that we need to develop these comprehensive models that synthesize our understanding of interactions between the natural and the anthropogenic world. That's a lot of the work that I talked about before. I haven't touched much on human hydrology interactions or human water interactions, but that's very, very important. The challenges can include how can we quantify sustainable water supplies? How can we predict water-related hazards? How can we understand the role of water in the Earth system? And when we're thinking about these challenges, it's immense, right? When we're thinking about how can we understand the impact of nature-based solutions on the terrestrial carbon sink, or how can we predict harmful algal blooms in popular tourist destinations, etc. A lot of these modelling problems can exceed the capability of entire modelling groups, entire agencies, and in many cases, entire nations. So the challenge that we have is that we believe that we don't have the actionable predictive information and tools to address the wicked questions that are asked of us by our governments. So I'm going to talk about Canada to begin with. I'm going to pivot to the United States, and then I'm going to pivot to the world. From a Canadian perspective, we believe that there are obvious opportunities to coordinate the diverse prediction efforts across Canada by building a national community of practice in environmental prediction. So when we're thinking about the Canadian problem, the expertise and capacities scattered across research and operational groups and at different levels of government. Often for our academic contributions, we're organised as a haphazard collection of short-term projects. We often need to reinvent ourselves at the end of each project, and government capabilities are often unevenly distributed across provincial, territorial, and federal jurisdictions. So this has led to fragmented capacity, inconsistent resource allocation, and a lot of inequities in the predictive information that's available to marginalised and disadvantaged communities, and also a lot of duplicated services across river basins. When you've got a lot of river forecast centres in different parts of the country, water often does not respect the different jurisdictions, and there's a need for people to work together, especially for these larger interprovincial systems and the larger transboundary systems. Currently there's no systematic effort to coordinate our approaches, and that's very different to what we see in the European Union and the US. And with all of that as background, Canada stands as the only G7 country without national capabilities to predict environmental risks. So we've argued in various venues that it's very clear that the existing approaches that are advanced in universities, government departments, and the private sector are insufficient on their own, and we really need to pull these different threads together in a much more effective way than we have been able to do in the past. So we've argued that addressing these challenges requires a moonshot approach. This is linking back to what I showed at the beginning, is that the comprehensive numerical models that we have can only be developed by unifying approaches from modelling groups around the world. As I mentioned before, the problems are too big for us to do it by ourselves anymore, and we need to pool resources. I mentioned before that individual modelling groups typically only demonstrate excellence in a subset of their model, so we need to do a better job of bringing the different areas of excellence together in a much more coordinated way. And by doing this, it will enable the different modelling groups around the world to address the wicked questions on water security that we're being asked to address by our governments. So if we do this, it can provide a transformational change in our collective capabilities to provide information to support some of these wicked global water sustainability challenges. The method, and this is like going back to what I showed at the beginning, is that we want to unify the state-of-the-art modelling capabilities globally into modular and interoperable software that can be used and extended by modelling groups around the world. And we want to provide the computational infrastructure to enable research and operational groups to contribute their unique data, information, and knowledge to a community modelling ecosystem. The outcomes is that the capabilities, if we do this, if we are effective in this global moonshot, the collective modelling capabilities will far exceed the modelling capabilities of individual groups, agencies, and nations, and it will revolutionize the capabilities for groups to provide the predictive information that supports mitigating and managing critical water crises. So how can we do this? Our first foray into this, and this is what we showed in the commentary paper that I wrote with Al Petronaro and Bob Sanford, is look south of the border. In the United States, they recently developed in 2022 the Cooperative Institute for Research to Operations in Hydrology. This is a new cooperative institute for NOAA. cooperative institutes for NOAA, partnerships with universities, and they're really set up to be permanent. They're renewed every 5 years. This cooperative institute was funded at a level of $360 million from NOAA for the first 5 years of the institute. What CAIRO is doing is very, very different from other cooperative institutes. There's a number of other cooperative institutes in the United States. I did my PhD at one, actually, the Cooperative Institute for Research in Environmental Sciences series at University of Colorado at Boulder. The difference with the cooperative institutes and CAIRO in Alabama is first, that it's geographically distributed. We think this is really important for Canada as well, is that it includes a number of universities and private sector partners that are distributed across the country. The second is that it's an alliance between government, academia, and industry. It's government, academia, and industry working together to fuse computer science, domain science, and data science on problems that are societally relevant. The third, and this is really in the name, research to operations in hydrology, is that there's a direct focus on research to operations, and we don't see that focus in a lot of the other cooperative institutes. CAIRO has a number of research themes. The first research theme is on prediction science. The second research theme, this is the research theme that we're intimately engaged in, is advancing and accelerating community water resources modeling. The third research theme is on cyber infrastructure. And the fourth research theme, and we're engaged in this as well, is application of social, economic, and behavioral science and water resources. This is the decision science theme. A lot of where we see our work going on in the future is the connections between these two spheres, looking at the connections between prediction science and decision science, in order to ensure that the solutions that we're getting policy relevant and capable of addressing key societal questions. So what we have been arguing for is Canada's CAIRO, that we need a version of CAIRO in Canada that integrates capabilities across academia, the private sector, and government. We've been calling it CAPE for now, the Cooperative Alliance for Predictions of the Environment, but that could be changed as we're moving forward. So we want to tailor the approach of our southern neighbour to suit the Canadian context. We want to develop our own form of a cooperative institute that integrates research across Canadian universities, government, and the private sector. And it needs to be singularly focused on research to operations to research, support the prediction responsibilities of Environment Canada, as well as other relevant federal departments, provincial and territorial governments, Indigenous communities, industries, and municipalities. And this is emphasizing, what I said before. We're seeing comparable shifts to community modeling internationally. And historically, if we're going back, 10 or 20 years, the reason for community models was because complex models could not be built and maintained by an individual scientist. This is the point that we made in our commentary. Now, the reason for a community approach is that the problems exceed the capabilities of agencies. They can exceed the capabilities of nations, and that we need to do a much better job of pulling people together globally to address some of these most challenging prediction problems. So what we see CAPE as looking like is a shadow system for the operational systems employed by Environment Canada and the provinces and territories. that enables scientists from both the research and operational communities to rapidly develop and evaluate new modelling and prediction methods. So this is going back to, what I showed, a proof of life of modular and interoperable computational framework, an open process for the development of the community prediction ecosystem. And importantly, and I haven't mentioned this yet, is shared computing across academia, government, and the private sector. This is really, really, really important. Often, it can be difficult for academics to get time on government machines. It can be some roadblocks to include government scientists and some of the high performance computing facilities that are pushed forward by the Canadian government, and working with the private sector on government high performance computing facilities, university-led high performance computing facilities, can be very, very difficult. So we need a computational sandbox when everybody can come together and work together effectively. We also need to have solutions-oriented partnerships. So this requires that we're doing things differently at universities. What I mentioned earlier in terms of the Cooperative Institute is very different than current funding arrangements because it's viewed to be permanent. We're not reinventing ourselves at the end of each project, but we're building and nurturing long-term relationships between academia, government, and universities. If we're doing that, we're needing to climb the technical readiness level ladder, where operational forecasting is in technical readiness level 7, 8, 9, where universities is technical readiness levels 1, 2, 3, etc. What we need is for the partnership to be in the middle. We need the partnership to be at technical readiness levels of 4, 5, 6. To really be building and implementing these systems. To work at these technical readiness levels, you can't always do that on the backs of graduate students. You need more experienced scientists at the university who can work effectively on those technical readiness levels. So that's why I'm arguing here that in addition to having a long-term relationships between academia, government and industry, we also need to change the career structure at the universities to employ the research faculty that we need to increase the technical readiness of new technologies. This is the partnership bullet that I mentioned before. So Al Petriner and I have been popularizing these ideas. We both gave presentations at the Environment Committee in the House of Commons, where we were arguing that Canada should build its own cooperative institute for environmental prediction to address some of the most challenging environmental prediction problems that affect our safety and security, our health and our well-being. These presentations at the Environment Committee have sparked a lot of conversations that Al and I have been involved in as to how we can move this forward effectively. So what we argued at the Environment Committee is that we wanted two things. The first was a federal funding platform for environmental prediction and research to operations paradigm. We thought that should cost about $50 million per year. The second thing that we argued for was the computing. That's what I mentioned earlier, as to that we need dedicated computing that provides the computational sandbox for academia, government, and the private sector to work together on these challenging prediction problems. And a lot of this has been pushed forward by Francis Scappalacia. He has had the Bill 317, which is the National Strategy on Flood and Drought Forecasting. This is a private member's bill that's now passed the House of Commons. I think it's now at second reading in the Senate. When we look at what's in the bill, we can see a lot of synergies with what we had put forward in the commentary paper that we published a little over a year ago. So we're beginning to see some of these ideas gain traction, and really looking forward to see what the new era of environmental prediction might look like in Canada. A lot of what we have been doing has been pushing forward and building collaborations with different groups around the world. We receive funding from IC Impacts to build collaborations with our colleagues in IIT Delhi. And this is Manabendra Saharia. This is Manab here in the back here. And Manab is really developing hydrological prediction capabilities for some of the major rivers in South Asia. I think he's one of the key leaders on building environmental prediction capabilities in Asia. And we've been working with him to combine many of our tools to address some of the challenging prediction problems that we have in the Ganges, Brahmaputra, and other basins in South Asia. We've also been looking at developing new collaborations in the Pacific Islands, and this is extending to some of the vulnerable islands around the world. This is work that's still in its early stages, but it's beginning to develop and bear fruit. One of the key collaborators here is this fellow here, Tom Jambaluka. He's been at the University of Hawaii for a long time, and he's a driving force as how we can push this forward. We had the pleasure of hosting Tom Jambaluka in Calgary a couple of weeks ago, and talked in a bit more detail as to how we can move this forward. This is also connected with Cairo. And Steve Burian, who's the executive director of Cairo, has been a major part of a lot of these conversations. So if I sum up now, what we're interested in is we're interested in prediction science, but we're not interested in prediction science alone. What we recognize is that we have a number of climate threats that affect our safety, our quality of life, our ecosystems, our economy. We have different policy and management options that we use across different sectors and communities to address these climate threats. And what our focus is that how can we advance prediction science in a way that increases the capacity to predict threats and risks from hydrological change. We've got in Canada and around the world a lot of devastating floods, drought, algal blooms, and drinking water advisories. And the thing that's missing at the moment, and the thing that we're trying to build in Canada and globally, is the will and the agency to build and nurture more dynamic and effective community engaged in prediction science, so that we can contribute our expertise to address some of the key climate threats that we're facing. To do so will require bold and visionary leadership at all levels of government and academia. We're seeing some progress, and we're looking forward to the future. So I'll pause there and see if there's any questions or comments that people want to make at this stage.
Thank you very much, Professor Martyn CLARK. That is quite a presentation. I guess my first reaction will be, it's interesting, the recognition of the fact that a tree does not make a forest, and the fact that scientists are beginning to appreciate that now, speaking to the CSIRO initiative in the US and the Cape version, that you're trying to promote in Canada. That's a good one. Yeah, in terms of question, the first question is saying, well, after appreciating the fantastic work, the fantastic presentation, is asking, did you do any work modeling mining areas or post-mining areas?
Me personally, no. There has, in Canada, there has been a lot of work in the Athabasca River Basin. We include the Athabasca as part of our domain, but in the work that I have been involved in, I have not focused specifically on that region. Very, very important though.
Okay. Another question says, when using mechanistic models for numerical predictions, particularly to describe global scale trends and responses, how do you address data scarcity at the regional or local scale, which is common in many areas around the world and could affect global outcomes?
Yeah, no, that's a very, very good point.
Professor Nima, the person asking the question is also a colleague, Professor Nima Shokri from Germany.
Okay. This is a very, very good question. This is a problem that we also face in the north of Canada, and our approach to this, I should have really talked about our thread of uncertainty quantification in the presentation. Our approach is to really focus on quantifying the uncertainty that we have and propagating that uncertainty through the model and augmenting the local information that we have with the global data sets that are available. So we have done a lot of work on developing ensemble data sets of meteorology for North America and the planet. There's the ensemble meteorological data set for North America and the EM-Earth, the ensemble meteorological data set for planet Earth. And what that does is it combines the station information that we have with long-term reanalyses from numerical weather prediction centers to provide a number of equally plausible realizations of what the spatial meteorological forcing is. What we do is then we then propagate that through our models that are being applied globally, and we're able to identify the hotspots of uncertainty as to where our data scarcity is most prominent. That's on one side of it. The other side of it is on the theory. What we see when we're developing models that are applied globally is it's often concepts that are formulated in in places that have got more research resources and applied to countries that have got fewer research resources. So there's issues of environmental justice associated with that. And that the processes that are represented in the models are not necessarily, the processes that are important in the regions where the models are applied. We don't currently have, a lot of field information in a lot of the vulnerable areas of the world, and we do need more information in those areas. But when we're thinking about this in terms of like the applicability of theories in areas where we've got limited information on model processes, I think that really emphasizes the need for a broader set of research across the globe. Did that begin to answer the question, Grace? It's a very, very difficult question because it's multifaceted, but it's also very, very important. It's an area where some of our research is focused, but there's a lot more that needs to be dedicated there.
Yeah, thank you, Prof. Like you said, it's actually very complicated. We can't shy away from the fact that there are really data scarce, areas and testing the integrity of these models that we're trying to project in this area will be challenging, you know. But I believe you did justice to it as much as you can. If one needs to focus on the application of theory, you know, than actually probably grant truthing at this point. But for the sake of time, another question came in. I'll just read it. It says, really interesting work, thank you. Exciting to learn about Dr. Deborah Membro's new appointment. But here is the question. Are there plans to incorporate indigenous knowledge in your models?
Oh, so are we incorporating indigenous knowledge in our model?
Yeah.
That's the question.
Yeah.
Right now, no. But I think that's really a key opportunity for us to move forward, and I think incorporating indigenous knowledge is a key way for us to narrow the gap between models and theory. There's the breadth of information that we have, the intergenerational knowledge in a lot of Indigenous communities. It's incredibly useful and has a key role to play here. The way that I just find theory is very broad. It's the stories that we tell to describe the natural world. It's a very, very broad definition of theory. And the stories can come from Western science, the stories can come from Indigenous knowledge. And I think that we need to be thinking much more broadly about how we can incorporate information from multiple knowledge systems in the work that we're doing. So very, very important. Not something that we're focused on at the moment, but I can see a strong need for it.
But sorry, as a follow-on question before I take the next one, is there a way of incorporating indigenous knowledge now that we're pushing for CAPE in Canada, for instance, rather than later?
There would be, yes.
It's okay. I have another question from my colleague here.
Yeah, thank you, Grace, and thanks, Martyn, for a very exciting presentation and also the pathway for Canada to go forward. So my question is, what are you planning to two things? What are the time scale that you are envisioning for this modeling plan for Canada? And second, are you also planning to integrate the effort that you are putting in Canada with the other global initiative like European ECMWF or other global modeling efforts? Thank you.
Yeah, so a lot of what we do depends on funding, right? It depends on resources. So we have a number of projects that are ongoing. Some of the work that we have is in Canada. Some of the work that we have is in collaboration with the US. Some of the work that we have is in collaboration with India, etc. So those are all areas that we're able to dedicate people, dedicate some of the best people that we have to solve some of the modeling problems. So that's what we can work on implementation now. Now your question is also about vision. So and what's the timeline to be able to connect better, you know, with agencies around the world like ECMWF? You know, what's the timeline for Canada to invest more in prediction science? And you know, we don't have the answers for that. We're pushing forward on that, but we don't really know what the timescales are beyond our control. We're articulating the vision as best as we can. We're talking with a lot of people to refine what the vision is, but the vision has yet to be realized. When we talk to people about it, it is not a matter of if. Right? It's that this is definitely an area that we should be doing, that we really need to advance on these topics. We really need to pull together people globally in ways that have not happened before. We really need to do that. The question is how. being able to move from the vision to the implementation and have some explicit mechanisms that enable us to move forward on these topics.
Thank you.
All right, Dr. Manzo.
No, not at the moment, but if there are questions from the participants as well. So I'll give them the opportunity.
So, Professor Clark, thank you so much for your insightful and visionary and progressive views and thoughts and presentations. It's really good to have people like you and all your colleagues in Canada continuously encourage the government to do better and improve its capacity to better manage water. Canada's identity is tied to water. Canada has a lot to offer to the world. And based on that, I think, with all the interactions you have with the government, the creation of the water agency and so on, what is your thought about how Canada can help the world in the area of environmental prediction and water management in particular?
Water management in particular. So water management is the biggest gap that we have in the general models that we're developing that are being applied globally. And the work that we have been doing in our group, we have incorporated lakes and reservoirs in the model, rudimentary representations of water management, similar to what's been done by other modeling groups around the world. But to move forward with water management in earnest, as you know very well, Dr. Madani, we need to have the local knowledge, and we need to have the base global modeling capabilities, and then working with the local partners to understand, what the key water management infrastructure is, what the concerns are, how decisions are made, and being able to incorporate that in a local context. That problem isn't unique to water management. That's a problem that, as we had in the discussion with Grace, cuts across theory as well as to how can you ensure that the model has a good representation of the dominant processes in the region that's applied. And the biggest challenge that we have is to cross the boundary between general capabilities that are applicable everywhere to specific capabilities that are locally relevant. And bridging that gap is really important. In terms of economies of scale, it does not make sense to me for everybody to develop their own version of a locally relevant model. We need the global community in order to come together on these topics. I think I'm a little bit biased here, but I think in Canada we're providing some of the thought leadership. We're providing some of the computational capabilities to crack this nut. That we're building the capabilities that enable us to address these pressing problems around the world. We don't have it all in Canada, and being able to combine what we're doing, with other groups around the world is incredibly important in order to solve these local problems. I think that's going to come more and more as we're moving forward, is that the investment that we have and the relationship with UNU that we appreciate is really helping us to cross the science to policy divide. It's really helping us to have the vision that we have and work towards having that vision implemented and really begin to make a real difference in the world. So we appreciate the collaboration, we appreciate the partnership, and I'm very much looking forward to what we can do together over the coming years.
Likewise, we are very excited about this cooperation, and we know it for sure it would lead to, I think, contributions that are beneficial to the nation and the rest of the world. And this partnership, as we have agreed, we will not forget the opportunities that are out there for the Global South to be stronger and play a more, I would say, significant role in shaping the collective wisdom that we need to manage water in a more equitable way and a more sustainable way. And thank you. I take this opportunity to thank you and the rest of your colleagues and the leadership at University of Calgary for the major contributions you have made so far and will be making in the years to come.
Okay. Well, thank you very much, Dr. Mandani. Thank you very much, Grace. Thank you for the opportunity to speak, and look forward very much to the future collaborations.
All right. Thank you.
Thank you so much.
Thank you so much. So we'll keep in touch, and then hopefully we can do this very soon. You know, in the near future. Thank you so much, and warm regards to UNU Hub and Calgary.
Yeah, thank you.
All right. Thanks everyone for being a part of this presentation. See you again next week. Let's talk. Bye.